morning and welcome to our next lecture on computational heat and fluid flow. So where are we? We are considering now the finite volume method for one-dimensional scalar conservation laws. And we are considering the good enough method. That was the last what we did. And in the good enough method, we solve a Riemann problem. So the Riemann problem, that is, we consider our conservation law, ut plus f of u. So u is the conserved variable, and f of u is the flux function, usually nonlinear, equal to 0. That is with the initial condition, and the initial condition is u of x0 is equal to UL, and in the good enough method we choose here the value in the cell J at the time level n for x smaller than the phase that we consider. So here we consider the phase J plus 1/2. And the UR is then the UJ plus 1 at the old time level for x larger than xj plus 1/2. So that was what all this together, we took that as the equation 18. And then we solve this Riemann problem, and then we get the exact solution to that. For example, for the Invisib-Burgers equation, and if we have the exact solution, it is denoted here in the lecture notes by G, UG, and then we evaluate the flux function with that to get the numerical flux at the phase. In that case, the phase J plus 1/2. So that is a very good method, and however, for some situations, like when we go to the Euler equations of gas dynamics, we will see we would need to solve the nonlinear problem, which might take time because we have to do iterations. And it has turned out that it is usually not necessary to solve this Riemann problem exactly. We can solve it approximately. And the method that does that is the Upwind method, actually, and that we are going to consider next. So that will be then the approximation to Goodenogh's method. So the Upwind method. So we can say that the Riemann problem 18 that we have just looked at, that we actually need to solve exactly for the Goodenough method, that is 18, does not need to be solved exactly. So we can solve it approximately. Phil Rowe from University of Michigan, he has, when he was at Cranfield actually in the United Kingdom, he had an idea how to do that, and he did the following. So his idea was linearizing the flux function. That is, he was assuming that we can represent the f of u as the f of ul, that is the L there that we have been discussing, plus a characteristic speed that he determined in a clever way, times u minus ul. So that means when we are at u equal ul, we recover the flux at ul, and his idea was that when we have f of u right, that we should recover the f of u right. So, and that gives essentially a condition to determine this. So we have that with such that that this is true. And that gives us then a condition. We see it immediately when we have this condition, how we can determine the aj plus 1/2. So we'll come to that in a minute, but the outcome of that was that rho could simplify the problem. So that is Phil Rho. There is a politician also with name Rho, so when you Google, you should then look for Philip L. Rho. He solves the Riemann problem approximately, but he does it the following. He solves the Riemann problem for the linearized conservation. So that is the following. So he looks, well, like that. That is something that you don't need to remember, but for those who like the mathematical derivation, I think it's nice to see. So then it is this aj that we had determined here in the first place. We still have to say, give the expression for that. And then we determine now, so we first note that the aj plus 1/2 is constant. And it has this property. And we note that the u bar that we have here, that we have introduced, that is actually the difference between u and ul. So in the sense also that we have here. So he solved this linearized conservation law exactly, because that is a linear advection equation. So the u prime is just a variable. This is just a constant, so this is linear advection equation. We know everything about linear advection equation. So that is then solves the Riemann problem for exactly. So that is the point, and then we can get then the value of u prime, and if we know that, then we know also this flux aj plus 1/2 times the u prime, whether it is left or right. When it's left, then u prime is 0. When it's right, it is u right minus u left. But when it is u right minus u left, then we can insert it here, and that is then u right. So then we have f u right minus f ul is then this guy here. So we can use that to determine the flux in the end. And the result of all this is following. The result is then the Upwind method. So the catch is that we linearize the problem so that we can solve it without any iteration, and then we have an approximate solution of the Riemann problem. So then rho obtained by that the Upwind method. And we could also call it Rho's approximate Riemann solver, because the Riemann problem is not solved exactly but only approximately. For scalar conservation laws. For scalar conservation. And that is then the following. It is now then decided, actually by the sign of this aj plus 1/2, whether we get there the value to the left. The value to the left would be then, for the u prime, would be 0, and the flux that we would get then would be the f of ul plus, if we take this here, that would be 0. We would get the flux f of UL. So that we can take already as a result. So 23. And now I denote the flux by rho with the R. So the F is the flux at the phase K plus 1/2. And we would get F of UL if this characteristic speed that we have used is greater than 0. In the end, we will also take it if it's equal to 0, to have it on one side, but that is not the main point. The point is when it's positive, then we take the value from where the wind is blowing. In that case, we decide the wind direction by this AJ plus 1/2 that we get from this condition here. We still have to say what it is. So then we take the flux from the left, if the wind is flowing from the left to right. AJ is positive. If AJ is negative, then the exact solution then for our Riemann problem here will be 0 on the left and UR minus UL on the right. We will get the right solution. So, and then if we have that solution, then we have here the U right minus UL. And if we add that, and we have the condition, this condition, that F of UR is F of, let's see, well, yeah, here it is, let me see, so that here it is a little bit, well, this is the condition that we had from this here, and we want to have that this is true, that we get really the right, the flux on the right. So in any case, when we have here the U right, we should get the F of U right. And that is the case if we have the AJ plus 1/2 negative. So in that case, we will have the flux determined by the value to the right. So again, it is quite natural for an Upwind method to do so, but the catch is that we use this AJ that we get from this condition here. So it is, let me write it here a little bit better. So F of UL plus AJ plus 1/2 U right minus UL. So then it becomes clearer. So that is then determining from where the wind is blowing. And now we have, that is the main point, to determine this characteristic speed, which determines the sign. And that we do by using this condition here. So we say then, we continue with 23. So we get this Upwind method, which decides then on from where the wind is blowing by the AJ plus 1/2, and that we determine now. And that is, as we remember, the characteristic speed. The characteristic speed at the phase. Characteristic speed is the following. That is then the AJ plus 1/2. And that we take as 24. So in this condition that we have here, to give us, that we got from linearizing the Riemann problem such that we solve the problem that we want to solve, that determines the AJ plus 1/2. If this is not 0. So because then we can write it, we can see it, we can take this over, minus F of UL and divide by this. Then we get F of UR minus F of UL divided by UR minus UL if the states on the left and right are different. Otherwise we cannot do it. So if we cannot do this if we cannot do it when L is equal U right, then we cannot do it. But we must still have a condition, and the condition that we then take if UL is equal U right, that is the condition when we let here UR go towards UL. Then we see we get the differential. We get here then the F prime of UL or UR, it doesn't matter, if they are equal. So again, when we want to know what is happening when UR is equal to UL, we make the limit UR towards UL, and then we see we get the differential. We get the derivative of F with respect to U. So that determines then the characteristic speed at the phase j plus 1/2 for the Upwind method. So now we want to know what this will yield for the implicit Burgers equation. That is our favorite example. So then we check that and see which scheme we will get for that. First we check what will be the characteristic speed for the implicit Burgers equation. So that is for the implicit Burgers equation, just to remind you, f of u is u squared half. That is what we need there. So then the 25 aj plus 1/2 is equal to, you can already see what it will be, because this is actually the shock speed, if you remember, from the Rankine-Hughes condition. That is exactly what we would get if we would want to compute the shock speed with a discontinuity, u left and u right. That is, so we would get then this shock speed, and we can repeat that, what we have already done yesterday. We compute this now. The UR, f of UR is then the UR squared half minus the U left squared half divided by the UR minus UL. And then we see from the third binomial formula that we get out of this UL plus UR half. And that is if they are different. So this is here if UL is not equal to UR, otherwise we cannot do it that way. And if we want to compute this one here, we take the derivative of the flux function with respect to u. U squared half derived with respect to u is u. So then we get there UL if UL is equal to UR. And now you see if we let UR go to UL, then we get here 2 times UL divided by 2. So we get this result. So this result here is valid even if UL is equal UR. So we can use this result. So that is then we don't need an if statement. So that is then equal UL plus UR half. So no matter whether they are different, UL and UR, or if they are equal, we get this result. So that is the characteristic speed. A very simple result, simply the arithmetic mean. So, and from that then we can get the explicit Upwind finite volume method. So then we get from that the explicit Upwind finite volume method. And if we would do it in a general way, we could do it that following way. That would be then 26. We would have the ujn plus 1 is equal to the ujn minus, here we have multiplied by delta t divided by delta x, so we get that in this form. And then we have here the fluxes. We have then here now the upwind flux by rho at the phase j plus 1/2 that we have determined in this way, minus the corresponding upwind flux at the phase j minus 1/2. How do we get that? We simply have then here j minus 1/2, and then we have here j minus 1/2, j minus 1/2. We have then an ul will be then the value in the cell j minus 1, and ur will be the value in the cell uj. So we just do the Riemann problem at that phase, and then we get the flux. So that is the general expression. And if we want to specialize for the Burgers equation, then we can do that, and we can write that down what we get. So where now we specialize. Here this is general, but now we specialize here to write down these special fluxes for the inviscid Burgers equation. The inviscid Burgers equation. We have the following: the flux, the numerical fluxes from the Upwind method. And again, we look only at j plus 1/2 is equal to, and then we just take what we have learned here. If the wind is blowing from the left, decided by the characteristic speed, then we take f of ul for the inviscid Burgers equation. That is ul squared. And ul, that was in our case uj squared half. So now we remember that the ul was uj. And that is the case if the characteristic speed is positive. And the characteristic speed for the inviscid Burgers equation is this. So then we can say if A and if, and now the ul is the uj, and the ur is the uj plus 1. So if that is larger or equal than 0, then we take the value of the flux from the left. If, in the other case, we take the flux from the right, that is uj plus 1 squared half, if the characteristic speed is negative. So then we have the formula for evaluating the flux, the numerical flux for the Upwind method at the phase j plus 1/2. And again, if we would have j minus 1/2, we just shift the index by 1. Instead of j, we take j minus 1, j minus 1, here it will become j, this becomes j minus 1, this becomes j, j minus 1, j. So then we have the general formula. Okay, so then we know the Upwind flux for the inviscid Burgers equation. And if we have another conservation law, then we have to determine the characteristic speed in a similar way as we did for the inviscid Burgers equation. And then if we have the characteristic speed, then we just do the evaluation according to the direction of the characteristic speed. That's all. So it becomes relatively simple, and the catch is using the characteristic speed to decide on the wind direction. So now we would also like to express this without an if statement in a similar way as we also did for the linear advection equation. Remember, we had something similar. There it was the velocity. We had a temperature flux, a convective temperature flux, ut, and that was determined by the sign of u. And then we had also an expression where we could express that without an if statement. That we also want to do now to express the upwind flux without if statement. We do it for the implicit Berger situation. So then we can write the upwind flux that is the one that we have there for the implicit Berger's equation, 27, can also be written as, that is the following, 28. So the upwind flux for the implicit Berger's equation can be written as the average of these two fluxes. That is then uj squared half plus uj plus 1 squared half. If we would stop here, we would have the central finite volume method, of which we know it is unstable for the linear advection equation with the explicit Euler method in time. So that is then will not work. So we have to do something, and what we do here is we add numerical dissipation, and it turns out that we can do it in this way, that we have then here the uj plus the uj plus 1/2. So that is the modulus, the absolute value of the characteristic speed. And that we multiply by the difference in uj plus 1 and uj. So then we get this expression. Now, you can prove that yourself, that that is true, by considering the two cases. Either this is greater or equal than 0, then you can remove the absolute values. And then you should get this result here. If the characteristic speed is negative, then you replace this expression by minus. So you have then brackets, but with a minus. So you get a plus here with usual brackets. And then if you do that, you will see you will get this result. So you do the same thing as we did for the linear advection equation. We have the two cases. And you will see you get the right one. So that is then a way where you can avoid the if statement. And if u is changing sign, say that the characteristic speed is changing sign, then it makes sense to use this expression. If you know the sign, say you have all those positive values, then you know you can use this expression. And it's safe and it's more efficient, as you see. If you know it's all negative, you use this. And another thing is, it makes sense to compute these fluxes once. If you compute them for each cell, you have to compute the fj plus 1/2 and the fj minus 1/2. So if we have here our cells, we have j minus 1, j plus 1. So imagine you want to compute the flux here. You do that, use the formula. You do that here. But that's not necessary, because if you have already computed this flux, when you compute the flux in the cell, in this cell, you have it already. So this flux is then the plus flux for this cell, and here it becomes the minus flux. So you can use it. So the flux that goes out here it is for the j minus 1, this is j minus 1/2. So this flux is, you computed already here, getting out, but this is the flux then entering this cell. So you can use it. You have it already. So if you compute it every time, you do twice the number of flux evaluations necessary. So therefore it makes sense to have a, say, a for loop or a colon notation to be fast in MATLAB, compute the fluxes once and then use them. And you need, if you have nj cells, you need nj plus 1 fluxes. Because if you start here, the first cell, then you can associate your cell number to the left flux. And if you come to the last cell, then say the nj, the flux is then associated with that, but you need also a flux here. So you have nj plus 1 fluxes. But you can do that, and it is more efficient than computing the fluxes for each cell from scratch, so to speak. Okay, so then we have the flux expressions, both with an if statement and without. Now let us characterize the method. That is the explicit Upwind finite volume method that we have here. Of course, we have it, everything is entering then in here. And what I think I did not say, what I have to tell you, that the fluxes that we are using here are, of course, you should add that, are at the old time level n. So everything is at the old time level n here. Because we only know it when we come at this point, we know only the solution at the time level n, and then we know these values here only at the time level n. So uj and uj plus 1 are at the time level n. So that I indicated now here. So then we characterize the method, and if we do a consistency analysis, we will find out that the method is first order in time and first order in space, like the Upwind method for the linear fraction equation. First order in time because we use the explicit Euler method in time, and first order in space because when we have, for example, uj or the aj plus 1/2, the characteristic speed positive, we get just the Upwind method, just the same what you're doing now for exercise 3. You are considering for exercise 3 something that resembles this case here, because you have u negative. But no matter, it is a one-sided difference approximation that it is equivalent to what we get with the finite volume method, so that it is only first order in space. Regarding stability, then we can argue this is a nonlinear problem, so that makes it difficult. But we can use the fact what we know for the linear problem, for the linear affection equation. So the argument is we linearize the problem and get a condition for linear problems. And then that is a necessary condition for being stable. It is not a sufficient condition, but in reality, when we test it, it is usually working. We can use more powerful tools to show stability, but usually it is enough to do a von Neumann analysis for the linearized problem. And then we can take the condition that we got for the linear affection equation, we can apply that here. And then the condition is, as we saw already when we discussed the good enough method, we had also there a stability condition that the absolute value of the current number, which is then defined in that case by the absolute value of the velocity in the cell j times delta t divided by delta x, has to be smaller or equal to 1 for all j. So that is then the condition. So then you choose then a value that you want to have. If you want to have 1, that is a good choice, as we shall discuss for exercise 3 for linear affection equation. And then you use that, set that equal 1, multiplied by delta t, delta x, and then the delta t has to fulfill this condition. So we have to choose then this here as the maximum of all moduli in the problem to get the time span. And it turns out that the method with this condition is also TVD. So it is also TVD, total variation diminishing, when this condition is satisfied. And that is also a nice property. Okay, so that is something. So the method is useful. However, it has its problems. Let's see that. The example I showed you yesterday was the shock problem that was run with this method. Let's see. It was the E4 shock. We can look at it again. So it was this problem here. So that is now solved with this method that we have seen. You see, I chose the current number 1. So that means I chose the C equal 1. For good reason, because there the method is really best, but we have not the same velocity everywhere, so only for the fastest way I get these the good properties from current number 1, but otherwise it will be lower and we'll have numerical diffusion as we see at the corners. So that is what we see here, but the shock is fairly well resolved as you see here. So the general feature, also the rarefaction wave is okay, except for small errors at the ends, but otherwise that looks fine. However, if we go to another problem, let's see, and that is actually what we had also discussed in the course Introduction to CFD last term. We have a problem, and that is when we have just a very simple problem. Let's see. So let's see what this problem is. So we have here the initial condition -1 to the left of 0. So here we have x equal to 0, and here we have -1. And to the right we have, and even here we have a finite difference method, so we have here included the point. That is the advantage, by the way, with the finite volume method. We don't include the discontinuity there. We have +1 on the right. So then we let the thing go. And let me see, that was already the solution with the fix. So, because then we get a solution, the dots are numerical solution. They are not perfect, but they are close, and if you would do grid refinement, they would get even closer to the exact solution, which is the red line. But here I have done something. So what I should have shown you, what I do now, is the one where this fix is not done. So that is the no fix. And that is the same initial condition, but now I use the method as we saw it. I have not done anything. And then we get this result. You see the numerical solution stays on the initial condition. There is no change. And what we get here is an expansion shock, which is steady because the average of u left and u right at the discontinuity, -1 and +1, is 0. So it doesn't move. And can we understand that? Yes, we can. If we look in here, if we are at the discontinuity, we have here -1 and 1. So this gives 0. And these guys here with -1 squared and +1 squared gives the same. So that it gives then, in the end, we will get 1/2 out of that. And when we go at j -1/2, we will get exactly the same. because then we have at j minus 1/2, this will be minus 1 squared and minus 1 squared. So that means in the flux differences here, they will be 0 on the left and on the right. But that means that we do not get any change and we reproduce the solution from the previous time step. So we start with the initial condition, so it is repeated, nothing changes. So we get the wrong solution. And that is the problem with the Upwind method, that it does not recognize when we have a rarefaction wave. It interprets that as a shock, which is steady and it doesn't move. And that is wrong. So that is where what I told you yesterday, the rarefaction, the expansion shock, that is wrong. And the Upwind method actually reproduces this wrong expansion shock. So we have to get rid of that. And in the result I showed you before, I got rid of that, but I had to do something. And that I want to explain you what I had to do. It is called entropy fix. So we have to tell now the Upwind method, there is a rarefaction wave, you have to do something. And what we will do is, in this formulation, we will give this a value that is small but non-zero. So that it is enough that by this, you remember, this times this half times delta x is the numerical viscosity. So we give it some numerical viscosity, some extra numerical viscosity, but only in this situation where we need it. So that is then the entropy fix. So we can say we saw it in the example that we have here. The Upwind scheme, that is the explicit Upwind finite volume method, is not entropy satisfying. Entropy satisfying. And that means it does not satisfy the Lux entropy condition. To avoid the non-physical expansion shock, and the critical situation is when we have also here when UL is smaller than U0 and smaller than U right. If this is happening outside 0, then we get still the right results and the error doesn't influence the flux evaluation. So this is the critical point. So in that case, if we have this situation, the Upwind scheme has to be modified. So the Upwind scheme that we saw, we have it here, that is the Upwind flux actually here. Let me see, Upwind flux 28 has to be modified. And one way, that is the way probably mostly used, is so-called Harton's entropy fix. That is due to Armin Harton, who also was the one that came up with the total variation diminishing concept. Harton's entropy fix. And that is the following. The absolute value here, that we have here, that is the absolute value of, say, the AJ plus 1/2. That is the absolute value of UJ plus UJ plus 1/2 in the equation 28 for the upwind flux is replaced by something that we call Q of aj plus 1/2, where the Q of u, that is the equation 30, Q of, now I've used the A, okay, also do it like that, is equal to absolute value of A. If the absolute value of A is larger, equals some threshold value delta that we have to determine, and or it is A squared plus delta squared divided by 2 delta if the absolute value of A is smaller than delta. And so what does this do? It does the following. If we have the A here, that is our characteristic speed, and we have the Q of A here, the usual thing is that we have the absolute value. So that is the absolute value. Absolute value of A would be like that. But when the problem is that here we have the origin, the 0. So at 0 we get a problem. So we have at some point we have a threshold, say delta, it should be symmetric. Say we have here the minus delta. So in this region we modify things. So the Q of A that is then modifying, it puts in a parabola here. So then, what we have here, that is the absolute value, and the Q of A that I now make red, it's the same as the absolute value here, but near 0 it is modified. So we see here that the Q of 0, we get some value. And it turns out the value that we get, if that is 0, delta squared over 2 delta, we get delta half. So we get something. So that means even if that is 0, we get some numerical viscosity. So that's the catch. And the choice, how you can choose this delta, there is a good way, which is actually determined by the jump that we have here between UL and UR. So you can choose the delta, for example, as the maximum of the UR minus UL. You have to check this condition, and the machine epsilon that we discussed in one of the lessons. So that is just to avoid division by 0 when delta should get small. Okay, so with that is the entropy fix that I implemented to get rid of this. So, but in many situations you don't need it. You need it when you have these situations that you have on the left something lower than on the right, and when this is the critical thing. So when this happens, then it is critical. So otherwise this Upwind method is a useful method. It's just that it is of low order, and that we shall try to improve. There are other methods that are useful. I mentioned in the lecture notes, and you have it also explained in the book, the method by Enquist-Osher. So that is, there you don't need an entropy fix. So it is built in that it satisfies the entropy condition. Okay, so we shall stop here for the break, and then after the break we shall see quite a simple method, but which has also its disadvantages. Okay, but here we stop here for 15 minutes break.